Hey everybody, it's Ripley back again. Excuse me, I had to take a little sip of tea. Today we're going to talk about sequences. Now, sequences, by and large, it's going to be kind of a vocabulary section. There's a lot of vocab to this. You're going to want to make sure that you write down the theorems that we talk about and lots of definitions. But by and large, sequences are pretty simple to work with. All that a sequence is, and we talk about infinite sequences in calculus, sequences that aren't infinite are pretty boring because they start and they stop and they're boring. Think of a sequence as just being a box with a bunch of numbered, ordered, go away. Sorry, you guys, I'm going to have to get rid of that. I can already tell. With a bunch of numbered, ordered elements. So you'll typically see sequences written in this way, A1, A2, A3, and then dot, 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 and then you'll have like an A sub n, and then A sub n plus 1, comma, dot, dot, dot. You'll also just see this is written as the set of, excuse me, the set of A sub n, or A sub n, or the set of A sub n as n goes from 1 to infinity. But the thing that you got to understand about a sequence is it's ordered, it's numbered. So like I said, you got yourself a little box here, horribly drawn box, right? And inside, it's got an infinite number of things, but they're numbered. So you got A1, and you got A sub 2, and you got A sub 3, and over here you got A sub 4. So if you were to draw it out, you would be able to tell from which number, from which value in the order it came. All right, so enough said. Now I'm gonna make a sequence, and then we'll talk about sort of the behavior of that sequence. So I'm gonna say A sub n is equal to, let's do n over n plus 4. Okay, so this is equal to, if you think about it, it's going to be 1 over 5, because we typically start at 1. There's no rule that says that we have to, and that can be a little maddening, but convention says start at 1. All right, so this is going to be 1/5, and then it's going to be 2/6, and it's going to be 3/7, and it's going to be 4/8. That's a comma, not a plus, otherwise it becomes a series, and then it goes on forever. Now, this is a really, really important thing to understand. It's probably the most important thing to understand about sequences. You might notice that, wait a second, Ripley, isn't this guy just, if I take f of x equals x over x plus 4, and then I simply say where x is a whole number? And you would be exactly correct. That's all it is. Sometimes you'll see this written as f of n is equal to n over n plus 4. So really what we've done is I'm gonna change sequences really quickly, but really what we've done is we have cherry picked the positive integers off of this. So let's say, for example, we've got 1 over n, right? We know what this thing looks like. This is 1 over 1 plus a half, or excuse me, comma a half, comma a third, comma a fourth. And again, like I said, comma dot dot dot. If you know what the rule is, if you know what the sequence is from whence all these numbers came, then if I'm out here at 1 over 107, right, then it's pretty easy to say, okay, this was simply the 107th term created by this sequence. But the whole thing came from f of x equals 1 over x, which I know looks like yahoo, like that. And then all that we've done is cherry pick. Clearly my drawing is not going to be to scale. We've cherry picked x equals 1, x equals 2, x equals 3, that looks like a lambda, sorry, x equals 4, and then we just go through and we pop those points out of the function. Now what that says is there is a marriage, and I'm going to say this over and over and over. There's a marriage between the sequence and the function from whence the sequence came. So the sequence we could think of like that. All right, that marriage is really important because what it tells us is we can use the behavior of the function to dictate the behavior of the sequence. And once we have the behavior of the function and the behavior of the sequence, or we know that the behavior of the sequence is the same as the behavior of the function, we can do all sorts of cool things. Okay? All right, so that's an introduction to sequences. Now, that's basically what they are and from where they come. Let's talk about divergence or convergence of sequences. Now this is super easy. So all we know is this. We know that a sequence has an infinite number of terms and that the terms are ordered. right? We can go to the set of values, and we can determine, if we know the rule, we can determine exactly from where that order came, right? Or from where that elements came. So the way we determine convergence or divergence of a sequence is extremely simple. It's the same thing every time without exception. Now let's be clear. This is the sequence, all right? That's really, really important. It's not the series. We're going to get into series in the next section. And the difference between a divergent and convergent sequence versus a divergent and convergent series is vast, like oceanographically vast. So be really careful. Kind of set your intention. I know you haven't really played around with sequences a whole lot in this class for sure not, but even in prior classes. So you might want to have that sort of internal schizophrenic conversation with yourself of, is this a sequence or is it a series? So all I do is take the limit as n goes to infinity of a sub n. If this equals a number, you converge. If it equals anything else, you diverge, right? Now you may be saying, Ripley, wait, what do you mean by anything else? Well, let's go easy. Let's start with these two sequences that I built right here. Let's do this guy and this guy. I know that the limit as n goes to infinity of 1 over n is 0. Yay, smiley face, converge, done, thank you for playing. I know that the limit as n goes to infinity of n over n plus 4, degree at the top and the bottom, or I could see that this is infinity over infinity and use L'Hopital, which is silly, because I know if the degree of the top and the bottom are the same, then the limit is at infinity is the ratio of the lead coefficients. Man, I said that really fast, which implies, ooh, don't forget your smiley face, yay, converge. Now, sequences don't have to be pretty. For example, I can do something like this. I can do limit as n goes to infinity of, say, let's keep it absolutely as simple as possible. All right, let's do -1 to the n. Oh, I'm getting ahead of myself. Let's change, sorry, ladies and gentlemen, bear with me for a moment. Let's suppose that a sub n, the series, is equal, or the sequence, excuse me, is equal to -1 to the n. All right, now, this is where it gets a little confusing because we're not going to end up with unique terms, right? When n equals 1, I get -1. When n equals 2, I get 1. When n equals 3, I get -1. When n equals 4, I get 1, so on, etc., ad infinitum, forever. Now, this is one of those instances where you're like, well, Ripley, do I know if this is for n equals 4 or for n equals 2? Well, in that case, what we would say is any time that n was basically 2k, right, we're going to end up with a 1. Any time that it's 2k plus or minus 1, we're going to end up with, I guess it would be 2n, right? We'll end up with a positive 1, else we end up with a negative 1. All right. Anyway, what happens if I take the limit as n goes to infinity of -1 to the n? Well, what's that look like? All right, think of it as a function, right? Now, we know for a fact that what's going to happen is it's going to start down here. When n equals 1, it's going to be -1. At n equals 2, it's going to be +1. At n equals 3, it's going to be -1. 4, +1, etc., 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 right? You agree with that? So you may say, well, Ripley, it's got to be 1 then. No, it doesn't, because it pops down to -1. Well, then it's got to be -1. No, it isn't, because it's got to pop up. That is still divergent because it does not equal a unique number. And that is really, really key that you understand that. All right? Now, the fact that we're using limits, and I'm not going to write out all the limit laws because you already know them from way back in chapter, well, in whatever your textbook says. In ours is like chapter 2.2 or 2.3 where you get all your limit laws. Since we're using the limit as n goes to infinity of a sub n, you need to remember all your limit laws, right? Well, limit of the sum of the limit, limit of the product of the limit, limit of the quotient of the limit, except where the denominator is equal to 0, etc., etc. So make sure that you know all of those. Okay? Let's see. I mean, that's pretty much it. This is where we start as far as determining divergence or convergence. All right? Same thing. Oh, don't forget your squeeze or sandwich theorem, right? Your squeeze theorem says if a sub n is less than or equal to, I'll give you one theorem because you haven't seen this thing in a while. We don't use it a whole lot. It's kind of one of those more esoteric dealios. So if B sub n is wedged between A sub n and C sub n, and we know that the limit as n goes to infinity of A sub n equals the limit as n goes to infinity of C sub n equals L, right? Then what do we absolutely know has to happen with B sub n? This implies, limit as n goes to infinity of B sub n must also equal L, because if you recall from limits, right, here's C sub n, the big one. I should probably, since we're doing this out at infinity, let's make horizontal asymptotes as opposed to some weird value. So here's C sub n. Yahoo! This is C sub n. This is A sub n. Yeah! Sorry, I'm feeling a little crazy. It's Valentine's Day today, which is always goofy. Since B is always wedged between them, I don't know, let's pick the light one. It could be doing this, right? Yeah! Right? Now, this, I guess I'm being a little bit glib. My dark blue was my A sub n. We're not actually, I shouldn't write these as A sub n and C sub n. What I should be writing is this guy is going to be like, I don't know, we'll call this H of n. This is the function, right? And this guy in here we could call f of n. This is the other function from whence these come. And then this guy in the middle would be our, what do we got? We got what's left, g of n. And then what we're doing is we're going through, and like I said, we're cherry picking values, right? So if the sequence tends towards a value, or if the function tends towards a value, then the sequence must also tend towards that value, which can be said of, even though g of n, which produces b sub n, even though this thing's crazy, hoopty, difficult to behave, by virtue of the fact that we know that it's wedged in, or hemmed in, by a sub n and c sub n, we know we got to head for the same value, always. So again, the marriage between the sequence and the function is super key, okay? It's a big deal. Now, I'm going to give you kind of a funky one, and it leads to a useful, interesting theory. Excuse me. Let's say that a sub n is equal to -1 to the n over n. All right? So let's turn it into our, all right? All right? And so what do I have? When n equals 1, I got -1. When n equals 2, I have 1/2. When n equals 3, I have -1/3. When n equals 4, I have 1/4. When n equals 5, I have -1/5. So, not plus, comma, etc., etc., etc. All right? Now, the confusing part about this is that the sign is changing. We know that if it were just 1 over n, then it would head to 0, because we know that the limit as n goes to infinity of 1 over n equals 0. Now, it should be relatively obvious that in this case, if I take the limit as n goes to infinity, if I were to graph it, right, and just cherry pick these points, I'd start at -1, I'd go to -1/2, I'd go to, or +1/2, I'd go to -1/3, I'd go to +1/4, etc., etc., right? What I'm doing is I'm getting closer and closer and closer and closer and closer to 0. True? So I have -1 to the n over n, which should clearly be 0 as well. It's got no choice. However, there's an interesting theorem that comes out of this, and it says this: if the limit of as n goes to infinity of the absolute value of a sub n equals 0, it has to equal 0, otherwise all bets are off, then this implies that the limit as n goes to infinity of a sub n must also equal 0. So in this case, as soon as I slap on those absolute values on this, I get to this, I get 0, yay. All right? If it equals anything other than 0, you are in trouble. Let me show you why. Don't just take my word for this. Let's prove it. So if I let a sub n equal, let's go -1 to the n over n plus 1. We did this, remember we did this one before. I think I had n plus 4 instead. Now what's happening here? Well, we know that if I take the limit as n goes to infinity of n infinity of n over n plus 1, this is going to equal 1, which is not equal to 0. So this theorem is not going to work, but I'm going to show you why. So this, let's say that this is 1 and this is negative 1. Well, what's happening in this case? When I let n equal 1, I'm going to start down here at negative 1, right? Or negative 1/2, sorry. Negative 1/2. When I let n equal, did I do that right? If I let it 1/2, yep. If I let n equal 2, then what's going to happen? I end up with positive 2/3. So I'm going to draw my little horizontal asymptotes here. Positive 2/3, which is going to be up here a little bit further, right? Then I go negative 3/4 when n equals 3, right? So now what's happening? I'm heading down towards this y equals negative 1, while at the same time I'm heading up towards the positive 1, right? Does that make sense? Because as n grows, I get this thing heads closer and closer to 1, but its sign keeps switching. So we end up with the behavior way out here at infinity, we end up with the negative, it ends up behaving like negative 1 to the n. That's what it ends up behaving like, which we know diverges because the limit at infinity doesn't equal a value. So that's a useful theorem. It's not going to show up very often. You're not going to use it very often, but it's kind of one of those better to have it and not need it than need it and not have it. And now, guess what? You have it. Okay. Couple of more things and then I'll be done. I don't want to hammer you guys too much today, but there's some stuff that's important. If a sub n equals r to the n, all right, which means the sequence produced by this guy is equal to r to the n. Like, for example, let's say that r equaled 3, right? So that tells me that r, whoops, not r, dingus, 3 to the n is going to spit out what sequence? Well, when n equals 1, I get 3. When n equals 2, I get 9, 27, 81, 243, etc., right? Here. Now, is it relatively obvious that this guy diverges? If I take the limit, as it goes to infinity, it blows up to infinity, and we're done. How about r equals negative half? Right? Let's do that one. So negative 1/2 to the n, this guy here. When n equals 1, I get negative half, positive 1/4, negative 1/8, positive 1/16, negative 1/32, etc., etc. Now, it should be, again, relatively obvious that this thing is headed for 0. If I take the limit as n goes to infinity of negative 1/2 to the n, it should be easy to see that that equals 0. This converges. So what do we do with this guy? When do we know that it converges? When do we know that it diverges? Well, now think about that. Remember, sequences are married to functions. So really what we're doing is we're dealing with functions of the form f of x equals a to the x, right? F of x equals a, that's where we're going. Now that's confusing because of notationally speaking, I've got an a here and an a here. Let's use a different one. Let's use b to the x because that'll be less confusing, right? Because I got an a. I do not want to be, there we go, confusing. Ambiguous. Okay, so we're pulling off of these. Well, it should be obvious to see that if this thing is going to converge, what I need is a function that does this, right? I need some function that does that heads for 0. Well, when do we know that that happens? Well, that happens when b is between 0 and 1. Whoops, between 0 and 1, right? But it got to be less than 1. 1 to the x doesn't make any sense. It's just 1. True? However, that theorem that I just gave you actually tells me I can extend that to this. Since when r is between 0 and 1, I know that I'm going to get something that converges to 0, right? Because, I mean, think about f of x equals 1/2 to the x. We know that that looks like this. We know that f of x equals 2/3 to the x looks like this. It's very similar. Remember, they pass through 0, 1, and they head for the x-axis, right? Affectionately known as y equals 0. However, we know that f of x equals 3 to the x goes, well, bam, and takes off towards infinity rather quickly, right? Now, we already know that behavior between 0 and 1. Again, this theorem, if I take the absolute value of a negative 1/2, so if I have negative 1/2 in here for r, it's going to behave the same at infinity as 1/2, right, to the x. All right, I don't know if that's super confusing, but at the end of the day, when I have a sub n equals r to the n, we know if r lives between -1 and 1, this implies that a sub n converges. Else it diverges. It diverges. Else, in other words, if r is anything else, right? If it's 1 or above, -1 or below, we are done. Okay, two more things. A couple of more things, I guess. We're going to talk about increasing, decreasing, monotonic, bounded sequences, and then there's just the monotonic sequence theorem. Okay, we say a sub n is increasing if and only if a sub n is less than a sub n plus 1 for every n. Okay, makes sense, right? A sub n plus 1 is going to be bigger than. So, for example, the n. That's an that is if I let a sub n equal 2 to the n, that is an increasing sequence, right? 2 squared is clearly bigger than 2 to the first, 2 cubed is bigger than 2 squared, etc., etc. So I've got, we say, I'm not going to rewrite that. What am I, a moron? A sub n is decreasing if and only if a sub n is greater than a sub n plus 1 for every n. It makes sense. Hey, guess what? What's an easy way to prove that a sequence is increasing or decreasing? If only there was some sort of, marriage between sequences and functions, I can determine when a function, when f sub n is increasing or decreasing, I simply take a derivative. And since f sub n, or f of n, I keep saying sub n, sorry, if f of n equals a sub n, and f primed of n is less than 0 for every n, guess what? This implies a sub n is decreasing, all right? Which is kind of nice. All right, if a sub n is strictly increasing, or, that's biggie, decreasing. It's strictly though, because you can have increasing sections of a sequence, just like you can have an increasing section of a function from whence the sequence comes. Strictly increasing or decreasing, that means they decrease throughout, or they increase throughout. All right? We call a sub n monotonic. And not like monotonic when somebody talks like this and makes you want to poke your eardrums out. All right? A monotonic sequence means it is strictly increasing or strictly decreasing. All right? Now, one more thing. If a sub n is greater than little m for every n, we say a sub n is bounded below. Bounded below. In other words, as you can probably see, there is no value of n such that a sub n is going to be less than m. So, for example, we know that 1 over n, a sub n, is bounded below by what? 0. By 0, right? Remember, so long as I plug in n equals 1, n equals 2, remember this guy just looks like 1, 1/2, 1/3, etc., etc. It's bounded below by 0, right? It's also bounded below by -15 pi, but 0 seems to be the most convenient accumulation point, as it were, below which this guy cannot get, all right? Similarly, if a sub n is less than capital M for every n, say a sub n is bounded above. Above. Now, there's a cool consequence to this. All right, but let's talk about 1 over n again. So a sub n equals 1 over n. What is a sub n bounded above by? Oh, and I guess that we can actually use equality on this. We're allowed to use equality. Okay. What is A sub, sorry about that, I just forgot. What is A sub n bounded above by? Well, it appears to be bounded above by 1, right? Because from 1, I decrease. How could I show that? I could take a derivative. There's a million different ways, right? So this is bounded above by 1. All right? So that's easy enough. Bounding is easy. They behave very much like least upper bounds, greatest lower bounds. It's also bounded above by 10 or 17,000. But you usually want to grab the least of the bounds above, which is referred to as the least upper bound. You also want to grab the greatest lower bound because it's just simpler, right? You want to, all things being equal, the parsimonious solution is usually the best, or the simplest solution is usually the best. It's also typically the most elegant, that whole Occam's razor thing. All right, one last thing. A consequence of monotonicity, or a monotonic sequence, and a bounded sequence is something called the monotonic sequence theorem, or MST. It says all sequences. Oh, you know what? I'm getting ahead of myself. I forgot one thing. If, you can probably see where this is going. If A sub n is bounded both above and below, this implies A sub n is simply bounded. So there's a difference between being bounded above and being bounded, or bounded below and being bounded. To be bounded, you have to be bounded both above and below. Wow, that's a lot of B's. That'll make you crazy. Now, that leads to the monotonic sequence theorem. It says if A sub n is monotonic, and bounded, this implies A sub n must converge, which makes sense, right? So think about this. Let's think about it. Let's not think of it as A sub n. Let's think of it as f of n. All right? All right. Now, I guess we should think of it as A sub n. Here's my m. Here's my big M. Here's my little m, right? We're monotonic. So I either have to increase or decrease, right? I don't have to do it uniformly, but I have to be decreasing throughout, which means since I'm bounded below by something, I'm either going to head for this as a horizontal asymptote, or I'm going to head for a value that's a little bit bigger than this, or quite a bit bigger than this. But one way or the other, I can't get below this. I'm not allowed to diverge. But you may say, but Rivley, wait, why can't I go woo, 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 like that -1 to the 1? Well, then I'm not monotonic, because I would be increasing, then decreasing, then increasing, then decreasing. Likewise, if I'm increasing but bounded above like this, then I got to head for m or some value slightly below. Now, is it possible for something to be bounded above but not below? Well, yeah, if a function like 1 over n minus 1, right? I know that at infinity from the left-hand side, this thing heads at 1 from the left-hand side. If I think of this as 1 over f of x equals 1 over 1 minus x, I know, or let's do, sorry, x minus 1, not 1 minus x minus 1, I know that at 1, this thing's got a vertical asymptote, right? So this thing goes like this. I know it looks like that. So I know it's bounded below by 0, but it's bounded above by nothing, because at 1, it heads for positive infinity on the right-hand side, which, since we're talking about the whole numbers, we're talking about the positive side. Likewise, I could just stick a negative out here, and then what happens? I get exactly the same problem, only it goes like that. And at 1, this is x equals 1, or n equals 1, I have the problem of infinity. So I cannot be bounded. Cool. All right, that is the end of my little spiel, my little lecture. Sorry for all the vocab, sorry for all the weirdness that some of these terms you've probably never heard of, but they're going to be really useful, and they're going to be super common in the way in which we speak about sequences and series, which sequences sort of lights the candle on everything, and then series just we're just going to tack onto it when we start adding everything together. All right, anyway, thanks for your time and attention. Have a glorious day, and I'll see you in class tomorrow. Bye.